everyone. Today we're looking at notes E-2, domain from an equation. So we've talked about domain from a graph, and today when we're doing domain from an equation, we're going to kind of tie the two in together. So remember, when you're reading the graph for the domain, you read from left to right, and you're asking yourself as you chug along from left to right, is there some ordered pair, is there some coordinate on the graph that I'm looking at? Is there some coordinate that uses this x value as you go? And if you look at this quadratic graph here, you'll notice since this graph spans all the way left, all the way right forever, that means that every single x value gets used. Okay, so hence the negative infinity to positive infinity for the domain. However, whenever you look at this rational graph, and notice that I've added the asymptotes in here. So there weren't asymptotes added because this was literally a snapshot from like a graphing calculator. And as you know, the graphing calculator does not tell you where the asymptotes are. You need to figure that out. Okay, so I've gone ahead and I've added the asymptotes to help us find the domain. So if you look at this little red piece down here, and as you read the graph from left to right, you ask yourself, are these x values over here being used? Is there some point on the graph that uses these x values? And the answer is yes, we're using these x values, and we use all the x values until this little piece here becomes kind of bound horizontally. Vertically it can go down forever, but horizontally it can't pass, cross, or touch this vertical asymptote here. So we definitely we span from negative infinity all the way to 4, okay, and then we have a parentheses because we can't touch at 4, can't cross, can't touch. And then this piece here picks back up also at positive 4. Again, this piece will hug this asymptote. It'll get real close, but it will never cross, never touch. So at 4 we have a parentheses, and then this piece here continues forever to the right. So therefore we span all the way to positive infinity. So now this is a square root graph. It's a transformation of the square root parent function. Okay, and I just want to remind you, since there's not really a dot there, but you can think of it as a dot. We strike at this point here. Okay, so that is like a closed circle dot, and then here, over here, we have an implied arrow. Okay, so I kind of drew it darker so you can see. So my domain for this graph, the x values being used, start at positive 1, and that is a bracket because we strike at positive 1, and then it goes forever to positive infinity. Okay, so now let's get into today's lesson. So first we will name each function, and then we will state the domain using interval notation. Okay, so on number 1, let's name this function. What kind of function is that? That's a linear function, right? So that's a linear function in slope-intercept form, y equals mx plus b. Technically, that's a y, right? And so think about that. That is not a special case. It's not like a straight vertical line or a straight horizontal line. That's a line with a positive slope. So when you have a line with a positive or a negative slope, not a zero slope or an undefined slope, of course, that line is going to go on forever. So therefore, your domain is going to span forever, negative infinity to positive infinity. Okay, that's your domain. All right, let's look at number 2. On number 2, we have a quadratic function, right? A quadratic equation. So let's write quadratic first. And we knew it was quadratic because the highest exponent we had on a variable was 2, so x squared. All right, and then think about any quadratic graph. So think about this graph and think about any quadratic graph. If I stretch, shrink, reflect, shift, if I do anything to this graph, is the domain still going to be all real numbers? Yeah, it's still going to span all the way left, all the way right forever. So any quadratic graph, as you remember from Algebra 2, has the domain of all real numbers. Well now, so we're thinking graphically. Let's talk mathematically today, looking at the equation, because that's what we're supposed to be doing today. Let's think about why both of these domains are all real numbers. Well, essentially, when you think about it algebraically, more or less, I guess is the best way to put it, from an equation algebraically, is you're thinking of what can x be and what can it not be. Are there any restrictions on what I can plug in for x? Okay, and the answer here is no, there's no restrictions on what I can plug in for x. I can plug in any real number I want for x. Okay, it wouldn't maybe be fun to work with, but I can plug in any negatives, positives, fractions, decimals, any number, any real number I want, I can plug in for x. There's no restrictions. Same here. There's no restrictions for what I can plug into x. I can plug in any number I so choose. Okay, that's why our domain is all real numbers, because I can pick any domain, any x value, remember domain is x, I want, and plug it in here. There's no restrictions. Okay, let's talk about number 3. So number 3, as you can obviously tell by the absolute value bars, is absolute value. And remember that that graph looks something like this. Similar to quadratic, no matter how I stretch, shrink, reflect, that graph, shift, doesn't matter. The domain is going to be all real numbers. And so that makes sense graphically, but it should, now that we've talked about it, also make sense mathematically, because if you look at that equation, is there any restriction on your input? Now in this case, I don't know why, but this handout has y for the input, and I don't like it because we're dealing with domain and range, and that can be confusing, but our input is y, so therefore that's what we're talking about when we're talking about our domain. Okay, so is there any restriction on what this input can be? And at home you might be like, oh, but absolute value can't be negative. No, my input here can be negative. It's just when I find the absolute value of that value, that would be a positive output. We're not talking about outputs, we're talking about inputs. Is there any number that I can't plug in here? Is there some rule? The answer is no. I can plug in any real number that I want. So therefore, graphically, mathematically, it makes sense my domain is all real numbers. Okay, last one here. So what kind of graph is this? What kind of function is that? It's cubic. I'm really testing your knowledge today, aren't I? Cubic. Okay, so that's what that guy looks like. And again, we're spanning all the way left, all the way right forever. Okay, and that makes sense that our domain for this graph is all real numbers. It makes sense mathematically because is there any x value or input that I'm not allowed to plug in? And the answer is no. There's no rules on what I can't plug in. Now that we've talked about all the all real number cases, or not all of them, some of them, let's talk about the more restricted cases. So your rational cases and your square root cases. So let's talk about those mathematically and not just graphically. So rational functions. Let's remember the PF, the parent function. What is the rational parent function? Remember, y equals 1 over x. So that's the rational parent function. So what restriction do we have about x in that case? What's our restriction, y'all? I'm going to write it real big over here. Our restriction is that the denominator cannot equal 0. Why? Why can we not have 0 in the denominator? Well, it's not allowed. You can't have 1 over something. You can't have anything, 1 over something. You can't have 1 over 0. You can't have any number over 0. 0 in the denominator is not allowed. So in this case, we are going to have a restriction on our input. We can't have 0 in the denominator. So let's first start with rational, and then we'll press on to square root. Okay, so let's start with number 6. I'm going to skip that because we just don't have time to do them all. All right, so again, let's look at this function. So what are the restrictions if I don't know how to graph this, and at this point we don't? You will learn, I promise. But if we're talking domain from an equation, what restrictions do we have for our input? And the restrictions are that what's in the denominator cannot equal 0. So in this case, x cannot equal 0 because that's what's in the denominator here. And in this case, x minus 5 cannot equal 0. This is already good. We're solved for x here. On this one, we need to move over the negative 5 and make it positive 5, and that gets x isolated. So now what's required, I'm not asking you, well, I am asking you nicely, but I'm saying it's required. So please do it. Okay, draw your number line, put your values on the number line, make sure you have them in the right order. 0 goes first, obviously, left to right, 5 next. Then you're going to put your points on 0 and 5, and then you're going to ask yourself, okay, are these closed circles? No way, because we can't, x cannot equal 0 and x cannot equal 5. I can equal anything else, don't you agree? So I'm going to shade everything else, because I can equal anything else, but I can't equal 0 and I can't equal 5. That number line tells you what to write for your domain. Okay, and then from there, when you do your number line, I promise it's not so bad. So my domain is going to be negative infinity. The shaded region goes from negative infinity to 0. Then I can't use 0. Okay, and then union with, joint with 0. I can use anything from 0 to 5. Make sure you're using those parentheses because those are open circles. Union with, you can go anywhere from 5 to positive infinity. Right? So that number line, that shading on that number line tells you what your domain can be. And this should make sense that you can't have 0 here because that would create 0 in the denominator, and you can't have 5 here because 5 minus 5 would be 0, and that would be 0 in the denominator. So that on rational functions, that the denominator is where your restrictions come from. Okay, let's look at one more example of this type. So number 7. So again, in number 7, what's in the denominator, this x squared plus 7x, cannot equal 0. Okay, let's pause for a second. Can my numerator equal 0? Yeah, 0 over some number is okay as long as that number on the bottom and the denominator is not 0. But again, remember, the rule in math is that you can't have 0 in the denominator. So the only thing we worry about is saying that the denominator cannot equal 0. The numerator we don't care about. No offense, numerator, we just don't care about you. Okay, so now this is quadratic and not linear. This expression here on the left is quadratic, not linear. So here I need to factor out my GCF of x, and then I have x plus 7. And then set each factor not equal to 0. So x cannot equal 0, x plus 7 cannot equal 0. So here on this, x cannot equal negative 7. So when you draw your number line, you have, be careful here, you have negative 7 on the left. That's good. It's going to have to work. Negative 7 on the left and 0 on the right. Okay, and your circle here and your circle here. And you can be anything else, but you can't be negative 7 and you can't be 0. So that helps you write your domain. Okay, your domain goes from negative infinity to negative 7. Can't use negative 7, and then we use this chunk here from negative 7 to 0. And then we've covered this chunk, and then we go from 0 to infinity. And remember, you always read left to right. So I've kind of gone over into these sections here, but I don't think we'll need it. I think we'll be good. Okay, we doing okay, y'all? Let's move on to square root. So let's talk about square root. So what's our restriction on square root? So let's first refresh our square root parent function. So our square root parent function is y equals square root of x. So what restrictions can you think of for our inputs there? So here our input couldn't be 0 because the denominator cannot equal 0. Here, what do we have? What's our restriction? Can we put any number we want in here for the radical? Any number. Are you thinking about it? So the interior of a square root has to be what? Greater than or equal to 0. 0 is okay. We can take the square root of 0, but can we take the square root of a negative number? And you're saying, yes, I know we can, but what's the result? The result is an imaginary number. Okay, so we don't want imaginary numbers. So our restriction here is that the interior has to be greater than or equal to 0 because of imaginary numbers. Okay, so that's why I've got that in red. Okay, so let's start here again. We don't have time to do them all. Okay, so remember, here I'm going to use different colors over here. So our interior, so I'm going to do my best, because this is tiny, I'm going to do my best to just highlight the interior. So that interior, x minus 3, is where my restriction comes from. So x minus 3 has to be greater than or equal to 0. So that's where that comes from. Okay, the interior has to be greater than or equal to 0. So therefore, x has to be greater than or equal to 3. Okay, so when we draw our number line here, the only tick we need is 3. And then draw your circle. And in this case, it's or equal to. And then in this case, can I shade all over like before? No, we have to just be greater than or equal to 3. So in this case, our domain is just going to be from 3 to infinity. And we include the 3, hence the bracket. Okay. So how about this problem? So in this problem, again, we're worried about that interior. This interior here, this 7 minus 2x. I wish I had a different color. It looks okay on the screen. It looks worse in person. As I look up at the screen, it doesn't look so bad. Okay, so the interior, 7 minus 2x, has to be greater than or equal to 0. So then to get x isolated, I know it might be tempting to move that 2x over because it's negative, but don't. When you're working with inequalities, you want the x on the left. So negative 2x is greater than or equal to negative 7. And then divide by negative 2. A red flashing light should be going off in your head. When I divide by a negative, you flip the sign. Okay, so x is less than or equal to 7/2. So the only point I need on this is 7/2, and this time it is shaded, and we go less than. So then my domain here is going to be negative infinity to positive 7/2. All right, now to the fun part. You're like, what? I'm already having fun. I know, it's about to get even more fun. Okay, combining rational functions with square root functions. So every appearance of a square root, so no matter where you see the square root, it can be in the numerator, the denominator, just off to the side, whatever, wherever it is, no matter what, must be restricted. How do you restrict with your square root functions? Oh yeah, the interior has to be greater than or equal to 0. Every denominator, so if you're working with a fraction, every denominator must be restricted. How? The denominator cannot equal 0, right? Okay, so we don't have time to do all of these. I know, sad day, right? So let's go ahead and just do number 11. So let's kind of like look at this problem and talk about everything that's going on here. So in this problem here, normally we wouldn't care about the numerator. Normally the numerator can be 0, so we don't care, except in this case we have a radical in the numerator. So remember, for square roots, no matter where, every appearance, whether it be numerator, denominator, or if it's like off to the side here, like plus with that or minus or whatever, no matter where the radical is, you have to take the interior. So the interior is y plus 8. You have to take the interior and say that interior y plus 8 has to be greater than or equal to 0. Okay, so that's one of our restrictions. Now the other issue is the denominator, of course. Okay, so the denominator here, y minus 3, that cannot equal 0. Okay, other than that, we don't have any other restrictions. So here this would be y cannot equal 3, and here this would be y is greater than or equal to negative 8. So now that I've got two colors, the question is, what color do I do my number line in? Yeah, let's do it in purple. Okay, so make sure you're careful where you place your values. Negative 8 obviously goes on the left, 3 goes on the right. We can't be 3, so we don't shade it. We can be negative 8, and actually we're everything greater than or equal to negative 8. So when we shade, we're going to shade to the right. That's greater. We're not going to shade to the left. That would be less. Okay, so we're greater than or equal to negative 8, but wait, we can't be 3, so be careful. Okay, skip him and then shade past that. So our domain would look like domain negative 8 to 3, and then 3 to infinity. Okay, last one here if I feel like we're good with it. Okay, we're actually going to do 14. So this one can be tricky. Let's look at this one. So let's look at the numerator first. Is there any reason why I would have to restrict this in the numerator? And the answer is no. So I almost want to write this. Numerator doesn't need restrictions. There's no radical. So the only reason we messed with the numerator in this guy is because there was a radical. But in this guy, there's no radical, so we don't need to restrict anything in the numerator. However, this is what gets really funky and why I'm trying to use my colors as much as possible to help. So what's in the interior here, this radical in the denominator, the interior, so just the x plus 10. So just talking about the x plus 10, the interior, remember, has to be greater than or equal to 0. But then you also have the restriction that the denominator, so what's in the denominator? Well, what's in the denominator is the square root of x plus 10, and that cannot equal 0. So what's in the denominator cannot equal 0. Okay, so in this case, we square both sides, right? So then we get x plus 10. You know what I want to do? Hopefully you're not writing in pen, and if you are, you're writing in erasable pen, because I just thought of this. here's what I really want to write. I want to write the radical x plus 10 cannot equal 0. Then I want to write this again. So when you refer back to your notes, you know where that came from. It came from the denominator. Now here's where we show the work. So square both sides. Okay, so this will be x plus 10 cannot equal 0. So therefore x cannot equal negative 10. There we go. I feel better about that. Now on this would be x is greater than or equal to negative 10. So let's draw our number line. So on the number line, the only value we have is negative 10. That's interesting. Well, here this says x is greater than or equal to negative 10, but this says x cannot equal 10. So this x cannot equal 10 trumps the or equal to here. So trumps the or equal to. So meaning we cannot equal negative 10. This trumps that, because if we equaled negative 10, I know it's okay for the radical, it's okay to have the square root of 0, but not if the square root of 0 is in the denominator. Okay, so we know that. We can't have 0 in the denominator. So this not equals trumps the or equal to here. So this negative 10 cannot be or equal to, and we're just going to shade everything greater than negative 10. So the domain would just be negative 10 to infinity with parentheses. Oops, so sorry, y'all.